Hello everyone, my name is Matthew Silver, and today in what I'm sure is probably a shock, I'm going to be talking about my actual research, in particular some work I did to optimize lookups to reducers. Now, I know most of you know what reducers are, but I'm legally obligated to explain, so bear with me for a moment. Let's say we have a variable and we want to perform a bunch of updates to it. Addition in particular is probably kind of a bad example because it's commutative, but in general, this is something we can't do. Except we can. So it provides reducers which allow concurrent update aids to a shared variable. The reducer is defined in terms of a memory. Updates are accumulated in local views, which store serial segments of the updates, and then these get combined together when computations sync. Right, so if you're ready for the sample, let's take that addition again. We add half of it to one view, the other half to another view, and then we merge everything together at the end. Very simple, right? Now, reducers are implemented via hypermaps, which map reducer objects to local views. And the hypermaps, in turn, are built from the sparse accumulator data structure. But the key point is that in our implementation, span map consists of a view array where each element is a pair of 8-byte pointers to a local view and the corresponding reducer's memory. Empty elements are represented with a pair of null pointers. Whenever new reducer is registered, first we get a global ID number and store it in the reducer's ID num field. Then we allocate the area in the corresponding slot in the view array. And when we destroy reducer, the 16-byte slot is recycled. Now, let's get to the part that we care about. A reducer lookup can be performed in constant time, and it requires only 3 memory accesses and a predictable branch. First, we need to obtain the address of the span map. Then we need to access the ID num in the reducer object. Then we need to access index ID num of the view array. And finally, we need to check whether the pointer is valid. It's a really nice and simple system, except that's not what actually happens in the current implementation. Okay, let's condense that large code down to something a bit more digestible. First, we get the current worker. That's a function call. Then we get the reducer ID. That's the memory access. Then we have a branch to see if that ID is even valid. Then we have another branch to make sure that circ is even running. Then we have yet another branch to check if a tool is making us reduce. Then we have another memory access to get the current hypermap. Then another branch to check if that hypermap has been initialized. And then finally another branch to check if the lookup is occurring during an already existing hypermerged. Oh, I'm sorry, did I say finally? Nope, we have another call to finally get the local view, and then we have the branch to check if the view has been initialized. Yeah, that's a lot more than what was promised. So, how can we trim this down? How can we get rid of this branch? This is the part where I was actually coding. So, quick note on measuring things first. The real identity application benchmark are suites for reducers, and even if there are a bunch of variables such as the number of workers that are being run on that make measuring these speedups challenging. So we developed a scheme where we would take a micro benchmark, which accumulates updates into a global variable, and we measured 4 different executions of it. First, serial global, which is just the original micro benchmark. Then serial reducer, which is the serial benchmark but with the global variable replaced by reducer. This is just to test overhead when we don't have the search runtime running. Then we have search global, where we take the micro benchmark, insert a bunch of appropriate search verbs and search spawns, but we keep the global variable. We only run on one worker, so even though we're technically accessing it in a racy manner, everything works out fine. And then finally, we have the full search reducer version, which is the same thing as the search global, but with the global replaced by reducer. This is to test the full overhead with the search runtime running. In particular, we're going to be using 2 different micro benchmarks here. One of them is intsum, which literally just sums up the values in an array of integers. Here is the serial code for it. Again, we're just hammering through this array, possibly a number of times, and adding everything into a global or value. And the second one is fib, because we really can't do a talk on search without using fib. And, the serial version is exactly the fib we know, except instead of returning the value, we're accumulating it into a global variable. So now that we know level measuring, we can get to work on the actual optimization. Now, there are 2 main approaches to optimizing the reducer lookups. We can either make the lookups themselves faster, or we can make them happen less frequently. We'll get to that second option later on. We'll start with the obvious speed up to the lookup itself, which is the branches. There are 6 branches that weren't involved in the SPA hyperobject specification. Checking if the ID is valid, checking if we're even running search, checking if we have a search term running, checking if the hypermap has been initialized, and checking if the lookup is occurring during a hypermerge, and finally checking if the view has been initialized. So there's really nothing we can do about branch 1. That's an unfortunate mistake that programmers seemingly make all the time. Branch 2 is also necessary since silk can be toggled on and off, and if it's off, well, we have a problem because there isn't a hyperobject to access. Branch 4 would require a fairly, I don't really call it large, but a non-negligible refactor to the code to safely eliminate it. And branch 6 is an inherent part of the SPA algorithm. Now, branches 3 and 5, we cannot, strictly speaking, remove them safely. They do play a part, but they are almost never triggered. 3 obviously doesn't occur unless we have the tool running, and 5 is a mistake that programmers very infrequently make. So we can use them as a nice smoke test to see how much overhead these branches are inducing. So let's get some numbers. Fully unoptimized, IntSum has these runtimes. Serial global is just a hair over 1 second. Serial reducer is just a hair under 11. Silk global is about 1.5, and silk reducer is a hair under 15. Now, I know what you're thinking. Wait a minute, I've used reducers recently, and they don't have that much overhead. We'll get to that at the end of the talk, but for illustrative purposes, we're using IntSum with one of the default optimizations turned off to show how much the call overhead is being affected. So, our obvious change is that we can add branch hints to those branches, and that doesn't really have much of any effect. If anything, it may be a bit slower. And if we just simply remove branches 3 and 5, well, we don't see any speed up in the serial case. Naturally, that's because those branches are accurately tracked for whether or not silk is even running. But even in the silk reducer case, we only really see a fairly small speed up, about 1 second. Given how difficult getting rid of the other branches would be, this looks like a dead end. So, a more promising area to take on would be those 2 function calls. Remember, we have to get the current worker, which involves the call to circlets get TLS worker, which is quite literally just returning a shared memory variable. And the other one we have to do is to get the local view. Now, if you'll recall from the SPA lookup specification, that should theoretically just be indexing into the view map. In practice, we have a few other branches, some of which are totally duplicated from the prior hyperobject lookup. So that was promising. So we can get rid of the TLS local call just by declaring the shown variable as an extern and then manually referencing it. Now, getting rid of the map lookup function simply turns into adding in a branch to check if we are over the SPA capacity, which is a restraint built in for memory purposes, and then checking to see whether or not the slot is null. So let's look at the numbers again. Once again, we have that rather horrifying unoptimized performance. Again, I show you in the current implementation, and it's not actually that bad. We're just using this for illustrative purposes. So if we inline the TLS axis, then we chop off about 2 seconds from the serial reducer case, and we chop off about a bit under or 2.5 seconds from the self reducer case. So that's a good start. So let's then add in the spell lookup. So naturally that doesn't have much of an effect on the serial reducer case, because again, the spell lookup occurs after the check to see if silk is running. In the silk reducer case though, we chop off another for a second. So at this point, we're down by, about 3.25 seconds. That's pretty promising for what was ultimately a fairly small change. So we just inlet on 2 of the 2 interior function calls. What else is there that we can do? Well, I have an idea for you. What if we inline the whole thing? Yeah, that's right. OpenSilk has a nice mechanism that allows certain ABI functions to be automatically inlined at compile time. It has this file, silk2c inline.c, and when you build OpenSilk, what it does is it generates the necessary bit code for that, and then stores it away, so that when you're compiling a regular Silk program and you see, say, a reference to enter frame or something, it can go in and get rid of that function call. With a relatively small amount of code, and when I say small, I mean hacky small. Yes, it's not that much, but it also involves including a C file, which you know is the epitome of good code. And so as you do this will get the same effect for the hyperobject lookup. Now, before I tell you the final result, one more quick note about that code change. As you can see, there's something there called hyperlookup path. All that is it's a wrapper function around the interior of that final branch 6. The branch that occurs if the view slot hasn't been initialized. That has no function change, that is purely there to make the inlining easier. In fact, just about all of those extras are there for a similar reason. So anyway, here was a result again with the prior inlining. Here is a sanity check, just to make sure that adding those wrapper functions doesn't have any meaningful effect on performance. Then we do see a tiny bit of a slowdown there in the serial reducer case, but since the wrapper is after the check for whether or not we have silk open, I am 95% sure that was just noise. Unfortunately, I was running these tests on my personal computer, which has a handful of background applications. I tried to turn them off, but Windows is calling like that. So anyway, with the whole thing in there now, boy did we see quite a bit of improvement The serial reducer case gets optimized away to almost nothing, being just 3.5 seconds. And the self-reducer case similarly loses quite a bit of time. So that more or less exhausts the low-hanging fruit for speeding up the actual lookup function. And with that, we move on to the other half of optimizations. What if instead of changing the function, we just call it less often? And this brings us to the pure optimization. Now, word of warning, pure semantics were implemented in Arkansas or without my actually coding them. Regardless, I merely measured the performance benefit. And this optimization is based on the fact that when you retrieve a view of a reducer on the same computational strand, the simulation and memory will be returned. It'll be the same pointer, so you can largely omit the call in the first place, and the compiler can usually figure that out. So, let's go back then to IntSum one more time. Remember that awful unoptimized result? Well, the reason that you have probably never seen that overhead recently is the pure optimization. When you do that, you basically get rid of all of the overhead. And in fact, this optimization completely dominates everything else. So, if we throw on all those other optimizations, it really doesn't have much of an effect at all. Nothing that can be measured outside of noise. Now, I can imagine what you're thinking. If pure dominates so much, then what was the point of the other optimizations? And the answer to that is pure is not a magic bullet. Let's move on from IntSum to the other benchmark we talked about, Fib. So if we run that for an optimize, we get these numbers. The serial reducer introduces about a 2-second overhead, and the surf runtime introduces about a 12-second overhead. Surf plus reducer adds a further 2.5. So it's about constant, the reducer overhead. And if you include pure, you really don't get any benefit at all. The reason is the optimization can't go past function boundaries. It's really great if you have a loop, but it's not so great if you have recursion. But if we include those inline optimizations, we do see quite a benefit. In the Fib case, we cut down on the serial overhead to under half a second, and we cut down the surf reducer overhead to just a bit under 1 second. So that's a really nice performance. And this gets to why I will use it in IntSum only as an illustrative reason. Fib would have shown similar to the same improvements. They're just a bit harder to tell thanks to the overhead the surf runtime on its own introduces. We're still trying to find some additional benchmarks that will hopefully show just how powerful the pure combined with the inline optimizations are together, but hopefully this shows you how they are separately. Any questions?